All right, class, in this particular experiment, we're going to study the ballistic pendulum, and basically we're studying the conservation of momentum, okay? But we're going to also use the conservation of energy to study the ballistic pendulum. Now, we already know how to calculate the initial velocity of this ball firing out. Okay, we have ourselves a mini launcher here. This ball is falling out. We have a variety of ways to calculate this initial velocity. This is another way to calculate the initial velocity. What is the benefit? The benefit is this. If you have a projectile that's moving so fast that it's very difficult to get measurements on it, then you can use a ballistic pendulum. So what is a ballistic pendulum? You can actually have, and in this case I have some mass over here. It's a PVC pipe, and it has some plumber's putty back here. Okay, the initial velocity of this tube is 0, so it's at rest. We don't know the initial velocity of the ball. We have a pretty good idea of what it is, but we won't use that in this particular experiment. We'll only use it as a comparison. And so we know the mass of the ball, and we know the mass of the tube because we put them on a scale. So we fire the ball into the ballistic pendulum. Once we fire it into the ballistic pendulum, the ball is going to work itself into the clay, and it's going to cause this pendulum to move. All right? Both the ball and the pendulum will have some final velocity. We don't know that. So we'll have to come up with a technique to figure out the final velocity, because our goal is to calculate the initial velocity. So this is the first scenario, and let me show you what our equation is going to look like. We start off with our initial momentum, and we have our final momentum. So our initial momentum is the mass of the ball times the velocity of the ball. That is how we define momentum, mass times velocity. And then it's also going to be plus the mass of the tube times the initial velocity of the tube. This is equal to the mass of the ball plus the mass of the tube times the final velocity of both the mass and the tube. So in this particular case, we have the mass of the ball plus the mass of the tube. In the initial case, we don't have that kind of scenario. The ball is separated from the tube. Y'all see that? All right, good. Now, one of the things that we realize is that the initial velocity here for the tube is 0, so that means that this piece is just going to go to 0. Everything else can be accounted for. Therefore, we can write this. That's what those 3 dots are for. It says, therefore, we can write the initial velocity equals to the mass of the ball plus the mass of the tube divided by the mass of the ball times, and let me write that a little bit lower, times the final velocity of the ball and the tube. Okay? So that's great. We know the mass of the ball, we know the mass of the tube. Now we need to calculate the final velocity of both the ball and the tube. So this is what we're going to do. I'm just going to add a new sheet. And we're going to use something that we're already familiar with, and that is the conservation of energy. All right? We could not use the conservation of energy in the first one because the ball did work on the clay. We don't get that work back, so energy is not conserved. Work is extracting energy from the system. Okay? So here we go. I'm going to have our ball inside of our clay. Remember, it had this final velocity here, and we don't know what this is. We need to develop a relationship for that. The pendulum will rise like so, and it will have a second final velocity, and the second final velocity will be 0. So we're considering this when the pendulum rises in the air, and then it actually stops. So we basically have some fish line coming down like so. And the same fish line is connected like this, all right? So it rises in the air, okay? So let's go ahead and use the conservation of energy in this particular case. And the conservation of energy basically is saying that E initial is equal to E final. So the energy in the initial case is equal to the energy in the final case. So we're just going to use the kinetic energy and the potential, gravitational potential energy. So we have 1/2 mass times the initial velocity squared. And in our case, the initial velocity is not the initial velocity, it's the final. So it's this velocity. This is our initial condition right here. Then our final condition is over here. Initial, final. Okay? So this is going to be plus mg y initial equals to 1/2 mass times the initial velocity. Oh, not the initial velocity. I'm looking at I'm looking at what I just did. And so let me make sure that we understand this position right here is our initial height. Okay? And then we're going to have our second final squared plus mgy final. So our y final will be at this location. All right. So what do we know? Well, let's just take our origin. Let's set our origin right here. If we set our origin at y initial, that means that y initial is 0. So we know a couple of things. Y initial is 0. So if you multiply anything by y initial, it's going to be 0. Y final 2 is going to be 0. Well, it is 0. And so anything we multiply by that is 0. So therefore, we can write this equation. And you guys may be familiar with it. We know we can divide both sides by m. And that is that v final, in this particular case, is just going to equal to the square root of 2gyf. Lo and behold, it's the same equation we had for the conservation of energy when we shot the ball straight up. So the conservation of energy is more concerned with what's happening in the y than what's happening in the x when it comes to gravitational, okay? If we have some wind blowing or if we're, yes, okay. So we're going to use these ideas together. And let's go ahead and put them together. So we have this equation right now. All right. And you have v final in there. And we also have this equation, which is v final. We're going to substitute this into the aforementioned equation. Okay. So one more page. We should be able to be done with this. So our initial velocity is just going to equal to mb, the mass of the ball, plus the mass of the tube, divided by the mass of the ball. These need to be calculated first because it's in the numerator. You don't separate it. And then it's going to be times the square root of 2 times g times the final height. So all we're going to be looking for is this y, all right? And so this is the theory, and we'll use this theory to talk about, I'll refer back to this page when it comes to the Excel spreadsheet.